Hello everybody. In our series of lectures on basic electronics, learning by doing, let us move on to the next. As usual, let us first recapitulate whatever we discussed in the previous lecture. You might recall, as you see on the screen, we discussed about the applications of operational amplifiers, especially the instrumentation amplifier configuration, how it can be used for amplifying the signal from a Wheaton's bridge, and we also discussed how in a Wheaton's bridge you can have a transducer or a sensor, resistance sensor connected in the form of a bridge, can be used along with the instrumentation amplifier, so that you will be able to measure the different parameters like the strain or the temperature, etc. Then as the second application, we also saw the current boosters, like if I want the basic capabilities of the operational amplifier are limited in terms of the output current. In order to boost the current to much higher values like 1 ampere or even larger, then we must make use of what are known as pass transistors, and we discussed about the various configuration using, for example, for unidirectional current boosters and bidirectional current boosters we discussed last time. So now let us move on to the next series of applications which will involve nonlinear applications of operational amplifier. Till now we discussed about the applications of operational amplifier where the output and the input had a linear relationship, something like y is equal to mx or V out is equal to A into Vi. The output voltage is Vi, the input voltage, multiplied by A, the gain of the amplifier, then it becomes a linear device and the amplifier is basically a linear device. Now what we are going to do is some of the applications of operational amplifier in nonlinear situations. That means the output and the input are not related by a simple constant factor, like V out is equal to A into Vi will no more hold good, but the output will have some relationship with the input certainly, but it will be of a different kind. So let us see what it is. One of the simplest applications that I can think of is how we can compare two voltages, whether which is higher in magnitude or lower in magnitude can be detected. Such application circuits are useful in many situations. We will perhaps take up some examples and application of these circuits also at a later time. So because the monolithic op amps are inexpensive, versatile and reliable, they can also be used for applications where it involves nonlinear output input relationship. One of the simplest example, as I mentioned, is a comparator. A comparator basically compares two voltages applied at the two inputs, and the output will show which one is larger of the two or which one is the smaller of the two, whatever. Therefore the output can be a completely different shape of with reference to time compared to the input. That is what I want you to realize here, because there is no linear relationship. In the case of a normal op amp, for example in the amplifier, if there is a sinusoidal wave that I give at the input, the output will invariably be a sinusoidal output. Whereas in this case, if I give a sinusoidal input, the output need not be sine, it can also be a square wave or something like that. So especially in the case of comparator, you would see that when I give a sine wave, it will become a square wave, right. So now what I am going to do is, what is the basic principle of this comparator? Let us look at this basic principle. We all know about the operational amplifier. The operational amplifier, when you do not use any feedback, when you do not give any negative or positive feedback, you know it operates under what is known as open loop condition. Under open loop condition, without any feedback, the operational amplifier has got very high gain. The typical gain of one of the operational amplifier that we keep using 741, as you all know, is 10 to the power of 5, 100,000, and therefore now you know, if I connect to the ground one of the input, that is what you see on the screen, then inverting input I have connected to ground, and to the non inverting input I want to give a input voltage. Let us assume I give some DC input. Now we all know what is going to happen, we know the transfer characteristics of the operational amplifier we have discussed. So when I keep increasing this voltage V in starting from 0, you would find when I cross even a very small magnitude of the voltage above the 0, which is corresponding to the inverting input, you would find the output will become plus VCC or minus VCC as a matter. In this case, when the V input is larger than the inverting input, the output will become plus, because you see the input is coming to the plus input. When it becomes more positive than this, the output will become plus VCC, it will be amplified by the open loop, and therefore any voltage you cannot get at the output larger than the VCC in principle that I already mentioned to you, and therefore the output will saturate at plus VCC. If I now make the V in negative by inverting the terminals at the power supply input source and then keep increasing from 0 in the negative direction, you would find the, because it is becomes less than the positive inverting input, you will find the output will go to minus VCC, because now in magnitude the input corresponding to the inverting input is larger, and therefore the output goes to minus VCC. So you can therefore detect voltages which are larger than some minimum by looking at the output of the operational amplifier. When the output is plus VCC, you know it is larger than 0 volts, which is the one of the input for the operational amplifier, and when the output is minus VCC, you know the input voltage has gone below in the negative direction with reference to 0, and that is why you are getting minus VCC. That is also seen from the figure that is shown at the by the side of the circuit. You can see for all negative input voltage, this x axis is input voltage, y axis is output voltage, and this is 0. So when I go for input voltages less than 0, that is on the negative side, the output voltage is minus Vsat, which is actually minus VCC almost. And when I go on to the positive side, when I go on the positive side of the input voltage, you find it goes to plus VCC. So what you get is almost a vertical line here, but it is in principle not a vertical line. You know that it is the slope of this vertical line will be the open loop gain, and then this becomes the transfer characteristics which we have already discussed. Right. So the positive voltage produces positive saturation, negative voltage produces negative saturation. Now what is the minimum voltage above which, when it goes above 0, then the output will change to plus VCC? If you ask this question, then it is very simple to answer. We know the output cannot be more than the VCC or Vsat, and so Vsat divided by 10 power 5 will be the maximum input that I can give, which will be within the linear region, the slope. So V in minimum is plus or minus Vsat by AOL, where AOL is a open loop gain. The open loop gain is about 100,000 10 power 5. V saturation can be the power supply voltage plus or minus 15 volts or 10 volts as the case may be, and divided by this number will become a very very small voltage. So I have taken a typical example to show it to you. If Vsat is, let us say, 14 volts, the output swing of the comparator is from minus 14 to plus 14, and if the open loop voltage gain is 100,000 as we took as a typical value, the input needed to produce saturation is plus or minus 14 volts divided by 100,000, and that is equal to plus or minus 0.14 millivolt, and this 0.14 millivolt is about 140 microvolt. So, what you understand here is that the input voltage, if it is more positive than the 0 by 140 microvolt, the output will go to plus VCC, and if the input voltage goes below 0 by 140 microvolt, the output will go to minus 14 volts. So, the output is within the range of plus or minus 140 microvolt at the input, plus 140 minus 140, total 280. So, over 280 microvolts it will make a transition from minus to plus or plus to minus, and therefore that helps us to detect the difference in voltage when I compare two voltages within plus or minus 140 microvolts. That is the whole principle of the comparator. So, if I have one of the inputs at a particular voltage, in this case at 0, the other voltage when it goes plus or minus 140 microvolt, the output will go to plus or minus VCC, either plus 14, minus 14, or whatever is the case. So, you can see I can detect two voltages within a range of 280 microvolts, or to be precise plus or minus 140 microvolt. That is the basic principle of the voltage comparator. Now, it is also called, in this case you can see the circuit once more, one input is connected to the ground, therefore this is a 0. So, if I now make this voltage go from minus to plus, the input voltage, you would find I will be able to detect when I am crossing the 0 within plus or minus 140 microvolt, I will be able to get a change in the output from either plus VCC to minus VCC or minus VCC to plus VCC, depending upon in which direction I am increasing the input voltage. Whether I am increasing the input voltage or decreasing the input voltage while crossing the 0 will decide which way this VSAT will shift from one to the other. Therefore, this circuit is also called a zero crossing detector. It is able to detect whenever the other input crosses 0 by switching states at the output from plus to minus or minus to plus, right. You should always remember that this circuit is corresponding to open loop condition. There is no feedback here, and that is very important. Without any feedback only it works as a comparator. Now, to show precisely what I have done is I have shown another simple circuit where I have got a potentiometer which has got 3 terminals. One terminal is connected to plus VCC plus 15 volts, and the other terminal is connected to minus 15 volts, and the wiper which is corresponding to the variation is given to the inverting input or the non-inverting input, as the case may be, while the other input for the op amp is grounded. Now, you know what will happen at the output. Whenever I cross this plus 15 to minus 15 should cross somewhere at the middle of this potentiometer, where it will be very close to 0. So, when I move the wiper above and below that 0 point, you would find the output will shift to plus VCC and minus VCC, as the case may be, because I will be exceeding that 140 microvolt range while moving up and down, and therefore this is one way to see in the lab actually performing the experiment. I can use a simple potentiometer and move the wiper, monitor in the multimeter, and you would find it is changing from plus VCC to minus VCC. You can also do that by continuously giving a waveform. For example, I have shown here a sine wave. I can give a sine wave to one of the input and the other input can be grounded, then what will happen at the output? If the sine wave amplitude, for example, is about 1 volt typically, then what will happen? Can you guess? You would find whenever the sine wave input crosses 0 and goes above 140 microvolts, then you would find the V in becomes more positive, and therefore the output will become minus VCC. That is what I have shown in the circuit there. It becomes to minus VCC, minus 15 volts, and when the sine wave automatically comes to 0 next time and goes below 0 by again some 140 microvolt or so, then you would find it will again go to, because this will become less compared to this, the output will become plus VCC, and therefore the output will again shift to plus Vcc as you see on the graph. So, the bottom graph, the square wave that you see corresponds to the output, and the sine wave above corresponds to the input for any of these circuit. Now, what is happening here, V low and V upper, I have marked this point as VL corresponding to lower threshold or lower tripping point, and this one to the upper tripping point at this point, and these two will be 140 microvolt for this case when one of the input is connected to ground. But instead of connecting to ground, instead of making it a zero crossing detector, I can connect a battery to that fixed voltage of 1 volt for example in the second circuit. Then what happens, over this 1 volt, when it exceeds by 140 microvolt, the output will become minus Vcc, and when this input becomes less than 1 volt by about 140 microvolt, then the output will go to plus Vcc. So, this VL and VO now will be enhanced from simple plus minus 140 to 1 volt plus or minus 140 microvolt. So, then the transition point can be now shifted wherever you want. So, if it is 1 volt, when the other voltage exceeds the 1 volt by plus or minus 140 microvolts, then you will get a output which is a square wave. So, you can see therefore that you can also provide an additional bias or a level to the verification of comparison of the two voltages. So, that is exactly what I have shown in the next slide. The figure shows something what is known as a Schmitt trigger. When the input signal is periodic, as it is in this case because I have given a sine wave, the Schmitt trigger produces a rectangular output of a fixed amplitude. The amplitude of this is plus Vcc and minus Vcc, or plus Vsat and minus Vsat. So, it can be a sine wave as I already mentioned to you, or it can also be a triangular wave or any other wave, as long as the excursions go towards both positive and the negative voltages, and the amplitude is larger than a minimum of few microvolts, 140 and 50 microvolt, you would find the output will always be the square wave. It will always be a square wave between Vsat and minus Vsat, but the width or the period of this square wave that you get out will depend upon what is the threshold that you have provided for the other input. So, this is one simple example. So, I would like to show you that how a simple comparator behaves by actually going over to the demonstration lab and showing two examples. In one, I will use a millivolt source and vary the input voltage and show you that output changes from plus Vcc to minus Vcc, and in the second case I will give a sine wave input and show how it is converted into square wave at the output to realize the basic principle of operation of the comparator. Here this is the comparator. I have put two circuits here. I want you to first concentrate on this circuit to the right. So, you have a potential divider, a 10K and a 1K, and the midpoint of that is what is connected to the plus input, and to the minus the inverting input I am going to give an input from a millivolt source. This is a familiar millivolt source which we have used in number of our experiments, and I can vary the output voltage by making use of these knobs, and that is connected to the circuit at the input corresponding to the pin number 2, which is the inverting input. To pin number 3, which is a non-inverting input, I put a potential divider and with a 10K and a 1K, and I have connected the midpoint. This will be approximately about 1/10 of the voltage that I apply for Vcc. If I apply for 12 volts, it will be around 1.2 volts or so. That will be the threshold voltage. Now, we have to monitor the output voltage. For monitoring output voltage, we will use a multimeter. Now, the same circuit is wired here. You can see the 741, and the 7 is connected to the rail voltage, the plus Vcc, and the green corresponds to the minus Vcc from the pin number 4, and I have the potential divider 10K and 1K here, which is connected to pin number 3 corresponding to the non-inverting input, and to pin number 2 you see I have connected the millivolt source. This millivolt source red line is actually going to pin number 2 in the circuit, and the output is monitored by using this red wire, which is actually connected to a multimeter. The multimeter here is actually in the voltage mode, and it is concentrated, now shows 11.31 volt. That means it is positive. That means my pin number minus the 2, pin number 2, which is corresponding to inverting input, is lower than the 1.2 volts, and therefore I am getting positive VCC here, nearly 12 volts. So now if you look at the dial, you can see the voltage here is indeed about 1 volt, and therefore it is less than 1.2 volts, and that is why you are getting 11 volts. I am going to now vary the input voltage at the millivolt source by 1 volt, 1 more volt. That means it is going to become 2 volts. So when I do that, I want you to look at the multimeter, see what happens with the click sound. Now I have changed to 2 volts, immediately you see the multimeter has changed to minus 10 volts. That means it has gone to the minus VCC, because 2 volts is larger than 1.2 volts, and therefore the inverting input voltage is larger than the non-inverting input, and therefore it goes to minus VCC. To do that, I can also do in another way. Now I bring back to 1 volt and vary this continuously. There is another dial here which can vary continuously. So now I would like you to watch the multimeter as I keep increasing it. You find when I just move by very small extent, it has come to minus VCC. I again go back, you will find again it comes to plus VCC. I go back again, you would find it becomes minus VCC. So it is at this threshold that this happens, and if you measure this, it will be very close to 1.2 volts or whatever is the input at the positive input, that is at the non-inverting terminal. So this shows that the comparator is capable of detecting voltages within the range of 1.2 volts plus or minus 120 microvolt on either side, that I was mentioning to you, and therefore it can be used to compare two different voltages. Now what I am going to quickly do is modify the circuit and go to the second circuit. Now I want you to look at the second circuit. The second circuit here, where you find the plus input or the non-inverting input is connected to ground, and the inverting input you are going to connect a sine wave, and the output I have put simple load resistor 10 kilo ohms and monitoring the output. You know what is going to happen, I already explained to you, whenever the sine crosses the 0 and increases by even 150 microvolt or so, immediately this voltage will be larger than this voltage, and therefore it will go to minus VCC, and whenever this voltage goes below 0 by about 150 microvolt, again this will become less compared to this, and therefore because this is larger it will go to plus VCC, and so you will get a sine wave converted into a square wave, as I have already explained to you. Now the same circuit is put here, you can see the operational amplifier with the 7 connected to plus and the green line 4 connected to ground, and the input is connected to a function generator here, which can generate sine, square, triangle, all those things. It is put in sine mode and it is around 10k range. So this is around 1.6 kilohertz is a voltage. Now I have set the amplitude at some minimum position, and then the output is connected to an oscilloscope. The output is connected to the oscilloscope. As a matter of fact, I have connected to one channel of the oscilloscope the input voltage, and to the other channel I have connected the output voltage. So you can see the input is sine wave, and when I vary the amplitude, you see the sine wave amplitude is also varying on the oscilloscope, and what I get is a square wave at the output. This is the output. Now if you carefully observe, the 0 of the sine wave will be somewhere here, and so it has just slightly crossed that 0, immediately you find it goes to plus VCC on this side, and whenever this again crosses that point, it comes back to minus. These two are actually minus 15 and plus 15, or minus 12 and plus 12, something like that. If you actually look at the position here, it is 5 volts per division for the oscilloscope. So 1, 2, nearly more than 2 divisions are there, that means about 10 volts plus or minus is what I get here. So you can see it goes to plus VCC and minus VCC every time the sine wave crosses the 0. So this becomes a 0 crossing detector, and it is therefore also called a Schmitt trigger, because a sine wave is converted into square wave. The frequency will not change much, because when I, for example, when I change the frequency in the function generator, the output also changes, the output also modifies, that is all. So it is almost the same frequency, but the levels are very important, and therefore you also get some feature which is corresponding to some ringing. Now you see this is better, now you are able to see the thing. So you can see the voltage is now in 10 position. So it is about 20, the amplitude is 20 plus or minus 11 or 10, and therefore it is about 20 volts peak to peak. So this is again another example of how a comparator can be used for getting a sine wave converted into square wave. Having seen that, now let us look at some variations of the comparator circuit for some practical applications. One of the important thing that we always worry about is that we should not overload the input, because we can apply any voltage to the input. We try to connect some protection the circuits to make sure that the input is not increasing enormously. So if you see in the screen, you see 2 diodes are connected in opposition between the inverting input and the ground. That is, this diode is in this direction, the other diode is in the opposite direction. So when I connect these, what happens is, whenever the input voltage goes beyond plus 0.7 or minus 0.7, these diodes will be either forward biased, this will be forward biased, or when it is minus, this will be forward biased, and therefore this voltage at this terminal can never be more than plus or minus 0.7 volts, and that is good enough, because we have seen, because of the open loop gain condition, this voltage cannot be different from this voltage with beyond plus or minus 150 microvolts or so, and therefore 0.7 is 700 millivolt, which is a very large voltage comparatively, and therefore we will never have any occasion to go beyond 0.7 volts, and so this will provide a protection for the comparator, so that you will never overload the terminal beyond 0.7 volts. There is also another important consideration that you should take into account, and that is, we know even though op amp is a wonderful device, almost an ideal device, it is not quite ideal, in the sense it does have difference in the 2 input bias currents, there is an offset voltage and several other things that come because of the not being very ideal situation. So you would find there are 2 input terminals and the voltage is compared between these 2 terminals. The 2 voltages should be only precisely corresponding to what we set with reference to that. If it is not, then it will become more complicated. Therefore, when I have a input bias current variation, which is a very typical situation in any op amp, normal op amp, you would find that there could be a difference in voltage produced because of the input offset current or the input offset voltage. So these input offset voltage or the input offset voltage generated due to input offset current passing through the resistors that are connected to the 2 input terminal can sometimes exceed 150 microvolts on the plus side or on the minus side. When that happens, the output will switch state, even though it should not, according to the input voltage that I have applied at the input terminals. I hope you realize the situation. Therefore, we would try to make as much as possible that the 2 input terminals are equal in voltages before I apply an external input voltage. To do that, in this circuit, if you see on the screen, I have again used the 2 diodes in opposition, plus I have used a resistor between the inverting terminal and the ground. This resistor takes care of the input bias current differences between these 2. If I keep these 2 resistors the same, then you would find the voltage generated here and the voltage generated here will be almost equal, even though it is very small, because we are now talking of very small voltages between the 2 input terminals. And you would find the 2 diodes will make sure that the voltage between the two terminals will never exceed 0.7 volts plus or minus, and therefore this is another scheme to take care of the input bias currents, and the two diodes are there for taking care of overloading the input terminals. There is another small difficulty that we have with reference to the output, and that is the output is always plus or minus 15 volts or plus or minus 12 volts, whatever is the VCC. If that is the case, you find it is very difficult to use that for any useful application. So, at least if it is from 0 to some 5 volts or 10 volts, we might be able to use it for some digital applications and things like that. And therefore, how do we control the output amplitude to any desired value is what I wanted to indicate to you. You find in the circuit that is shown now, at the output I have connected a diode and I have also connected a RL, the load resistor. If we measure, the input is a sine wave about 25 millivolts amplitude, that peak amplitude, that is enough for us, because we require only plus or minus 150 microvolt above 0, and one of the input is connected to 0, therefore it is a 0 crossing detector now, and when the input goes beyond 150 microvolts or so, the output will become minus VCC. When it becomes minus VCC, this diode will be forward biased, and therefore it will be conducting, and I will have only about 0.7 volts as the output voltage, which is a voltage applied produced across the diode, and therefore it is minus 0.7, because this voltage will be negative with reference to the ground, because the current is flowing in the other direction, and therefore it is minus 0.7. And when I have the voltage going less positive, that is going negative on this side V in, you would find the plus will become more, and therefore it will go to plus VCC. For plus VCC, this diode is reverse biased, and therefore plus VCC will come out as such. So, what I have done here, therefore, by using this diode, I have cut the voltage on the negative swing. It is only 0.7 to plus 15, minus 0.7 to plus 15, it is almost like 0 to plus 15, and therefore this can perhaps be used in different circuits for digital applications and things like that. So, this is one way. It will also be still better if I can also control the two voltages on both sides, plus 5 to minus 5 or plus 3 to minus 3 and things like that. For that, we can think of another application, and they will this is the circuit which I show now, where I have used in the feedback two diodes, two Zener diodes to be precise, and the two Zener diodes, for example, I have used 1N749, which has got a breakdown voltage of about 4.3, and they are connected in opposition. One is connected in this direction, the other is connected in the opposite direction. Therefore, whenever I apply a sine wave, this cannot be 25 millivolt, it has to be much larger. So, whenever the output switches to plus 15 and minus 15, you would find these diodes will break down first. Zener diode, one of them will break down, the other diode will be forward biased. So, 4.3 volts will be appearing across one of the diode, and 0.7 will appear across the other diode. So, the total voltage will be 5 volts, and therefore you will get the output swing from plus 5 to minus 5 when I have this type of a situation. You can have a plus 5 minus 5 variation. So, this comparator with two Zener diode in opposition connected in the feedback can be used to limit the output to any desired value by choosing proper Zener diode with breakdown voltages. Now, you also saw in the demonstration that I showed that we need not have 0 crossing, but we can also have some reference voltage. We have used a potential divider R1 and R2, and the midpoint was connected, the same circuit we showed in the demonstration, and therefore this is again a method by which I can convert a 0 crossing detector into a comparator for comparing a threshold voltage, which can be chosen by properly choosing the R1 and R2 value. In the example I showed, R1 and R2 was 10K and 1K, so the threshold was around 1.2 volts. But if you choose, for example, R1 R2 equal 10K 10K, then it will be half of the VCC, maybe 7.5 volts or whatever. So, the reference voltage therefore is R2 divided by R1 plus R2 times VCC, and this is one way to change the thing, and you will have to have the capacitor there is used to speed up the operation, and therefore you must make sure when you use the cutoff frequency, then you must make sure that the ripple frequency of the power supply etc. will come into the game, and therefore the cutoff frequency of this bypass should be much lower than the ripple frequency of the power supply. So, if you look at the transition corresponding to the input output voltage relationship corresponding to this circuit, you would find it is minus V sat up to that V reference, and only at the V reference it goes to plus V sat, and because the V reference is positive, it is on the positive side. The transition happens at this 1.2 volts or 1 volt or whatever may be the reference depending upon the R1 R2 value that you have chosen. You can also have a very similar circuit. Instead of plus VCC I connect the minus, then what happens, the reference becomes negative voltage. When the reference becomes negative voltage, correspondingly the input output relationship will be shown as shown in the picture. You will find up to the minus V reference it will be minus VCC, and when you go beyond you would find it goes to plus VCC or plus V sat. So, one can easily choose the reference points to be either 0 or positive or negative by these options, and you can have the comparator to verify two voltages which can be either 0 or some other number on the positive or negative side. We have also, apart from 741, we have also comparators which are commercially available, because 741 is not actually meant to be a comparator. You know, the output swing cannot be too fast. Even in the demonstration I showed, you would find the transition from minus VC2 to plus VCC was not vertical, it had a finite slope, and that slope is due to, I hope you all remember, due to the slew rate of the operational amplifier. So, manufacturers have made comparators exclusively for comparative purposes, comparing voltages, and not for amplification, and therefore those will have much better slew rate behavior, and therefore I have given one example of LM339, which is an open collector device. The advantage of having an open collector device is to restrict the output voltage to any desired levels. For example, in this picture that I have shown, you have V in, you have R1 R2 divider to have a V reference here, and at the output I have connected a plus 5 volts through a 1K resistor to the output. So, this comparator is compatible to digital circuits, because now the output can never be more than 5 volts and less than 0 volts. So, because it is connected through an open collector output to a 5 volts, the output will be clamped at 5 volts and 0 volts, and therefore it becomes compatible to TTL device or digital circuits. The pull up resistor is around 1 kilo ohms. So, the transfer curve for that circuit will be 0 volts till I come to the V reference, and beyond that it will be 5 volts plus 5 volts. Now, all these comparators so far that I talked about will have transition occurring at plus or minus 150 microvolts, that I already mentioned to you again and again. But this plus or minus 150 microvolt is what is called hysteresis, for a reason which I will explain to you in a moment. It would be better in many applications to have this difference plus 150 minus 150 much larger than this small value. For example, plus or minus 1 volt or plus or minus 2 volts as the case may be. This is because in every circuit there is always the noise component, which are all unwanted signals coming from various sources all around us, and some of them are harmonic. For example, some of the transmission coming from different radio stations, television stations, etc. will all be sinusoidal, harmonic, but still we are not interested in them, therefore they are considered as noise voltages. there are other transient voltages coming from different devices like electric motors, neon signs and power lines and things like that, and therefore, they also will contribute to some fluctuations at the input. All these noise voltages are random, and therefore, they can either increase or decrease the input voltage randomly, and if it increases or decreases by more than 150 microvolt, the output will change even though my input voltage is not changing, because of purely because of the noise voltage. The magnitude of the noise voltage is exceeding that 150 microvolt limit, and therefore, the output switches automatically without waiting for the input to change. This is an undesirable effect, we do not want that to happen. So, what we do is therefore, to increase the hysteresis, the levels at which the voltage transition occurs at the output. The corresponding circuit I have shown here. What I have done is, from the output I have connected a potential divider R2 and R1, and I have taken the potential divided output to be given to the plus input of the op amp. So, this is actually a positive feedback, as you can see from the output I am giving to the plus side. So, it is called a regenerative comparator. This is also called regenerative comparator. Now, because I have connected like this, you know, something going to happen, very important and very simple thing going to happen, and that is V output will decide what the threshold or the reference voltage here is. The reference voltage here now is R1 divided by R1 plus R2 times V output, but the V output itself can be either plus VCC or minus VCC. Therefore, when it is plus VCC, this voltage will be R1 divided by R1 plus R2 times plus VCC, and when the output is minus VCC, this reference will become R1 by R1 plus R2 times minus VCC. And therefore, if for example, the typical demo that we showed, the R2 was 10 k, R1 is 1 k, so it was about 1.2 volt, and in one case it will be plus 1.2 volts, and in the other case it will be minus 1.2 volts, and therefore, V in whenever it exceeds plus 1.2 or minus 1.2, the output will change state, and therefore, the gap between the two transition will be plus 1.2 to minus 1.2, that means 2.4 volts. So, from plus or minus 150 microvolt, we have now expanded the variation to plus or minus 1.2 volts, which is a very large difference, and therefore, this 1.2 volts cannot be generated by any of the noise voltage in normal course, and therefore, we do not have to worry that the outputs switching state because of the input noise. So, this is also called by another name Schmitt trigger. Some of you might have studied in transistor circuits how by using two transistors one can make a Schmitt trigger, which is designed by the Schmitt, as the name goes. What the circuit does is, it is sensitive to some threshold voltage at the input, and the output will go to plus or minus voltages levels, two levels corresponding to the input, and there are two levels at the input for which this transition will occur, and the two levels are called LTP and UTP. LTP means low tripping point and higher tripping point. So, in this case, what we have LTP and UTP are the V reference voltages corresponding to plus B Vsat or beta Vsat and the minus B Vsat. These are the two tripping points, at which the tripping point is a point at which when the input voltage exceeds that, the output changes state from plus Vc to minus Vcc. Once you have the graph, you can see happens this way, the transition V output versus V input. If I draw, you would find till it comes to minus beta Vsat, the minus reference, the output is minus Vcc or Vsat, and at this stage it makes a transition and goes to plus Vsat. Once it goes to plus Vsat, the V reference becomes plus, and therefore, till when I come back with the input voltage, till I come to plus V reference, there is no transition, only at plus V reference there will be a transition. Therefore, you find in this graph is traversed along this direction, and it goes up, comes over here, and when it goes back by a different route. Therefore, this is called a hysteresis. Some of you may be familiar with the hysteresis graph that we get when we take a magnetic material through a cycle of magnetization. And if of course it will not be a square loop like this unless it is a highly ferromagnetic material like a ferrite or something like that. So, you will get a hysteresis behavior in those devices also. Similarly, we get a device hysteresis behavior, therefore, it is called a hysteresis, and the difference in voltage is what actually matters for us with reference to a comparator, and this is made to be like this because it can be unconcerned about the voltages corresponding to the noise. Okay, we can have two different types of circuits. You can have the non-inverting Schmitt trigger and the inverting Schmitt trigger. Right, the figure shows a non-inverting Schmitt trigger and the corresponding input output relationship, minus V sat and plus V sat you get, and you can initially showed you the inverting Schmitt trigger, and the UTP LTP in the non-inverting will be R1 by R2 times V sat and minus R1 by R2 times V saturation. So, the only difference is with reference to, in the other case it was R1 by R1 plus R2 times V sat etc. Here it is just R1 by R2 times V sat, and therefore, this also will help you to make a Schmitt trigger with a regenerative comparator. So, I will show you the demonstration with reference to a regenerative comparator, and then there are also other comparator designs and the applications of these comparator circuits in different situations, which also we will discuss later. Now, I will show you the demonstration. Now, I want you to look at the picture here. This is the circuit of a regenerative comparator, as I already discussed. So, you have from the output you have taken a potential divider 10K and 1K in the example, and the point potential divided potential is applied at the plus terminal at the input as a feedback. So, this becomes a positive feedback, and to the inverting input a sine wave input is given, and what you get of course will be a square wave, but now what is going to happen is, because it is a regenerative comparator, you will have, whenever this is plus VCC, this point will become some beta times plus VCC, and when it becomes minus VCC, the reference point becomes minus beta times VCC, and therefore, whenever the input voltage exceeds plus beta times VCC or goes below minus beta times VCC, that will be transition instead of plus or minus 150 microvolt as we had in the earlier cases. So, that shows that it has got a hysteresis. In order to show the hysteresis, what we have done is, I have taken this input and given to x axis, and the output I have given to the y axis, and I am trying to look at what happens in the oscilloscope. Now, I want you to look at the circuit. Again, this is a 741. You can see the plus VCC and minus VCC are connected to pin number 7 and 4, and the input is connected to a function generator, which we also saw previously, and this is now in sine wave, it is also in sine wave, and the output is connected to the input and the output are connected to the oscilloscope. I have used both the thing, I have put it in XY mode, and therefore, this is the sine wave, one of the channel, the other channel is the output. When I connect, what you see is exactly the transition hysteresis graph that I already explained to you. So, till it comes to plus VCC, there is no transition, and at that time it goes to minus VCC, and after it goes to minus VCC, the reference becomes minus beta times VCC, and therefore, till it comes here, there is no transition, and the transition occurs here. So, you can very clearly see the transition happening here, and this is the hysteresis graph that you get for corresponding to the circuit. When I remove the XY mode, what you see is the normal sine wave as the input and a square wave as the output. These transitions occur at two different reference points now, exactly similar to what we saw in the earlier case. In the earlier demonstration also we used a sine wave and we got a square wave, but the square wave transitions were happening at plus or minus 150 microvolt. Now, it is happening at plus or minus some other voltage, and that voltage is decided by the potential divider that you see in the circuit. For just showing to you, demonstrating to you that the V reference depends on the potential divider, in this place I have connected a 10K potentiometer. Therefore, now I am going to vary this potentiometer, and when I vary the potentiometer I want you to observe at the output of the oscilloscope to see what happens. So, now please observe the oscilloscope. Now I am going to vary this, see the oscilloscope, what happens. You can see the width is changing corresponding to these variations. When I vary this nearly by half scale, it is changing. Okay. So, what we saw is a demonstration of the regenerative comparator, where the input was given as a sine wave and the output is given as a positive feedback by having a resistor network R1 and R2, and when we changed one of the potentiometer, the output was also changing. That means the reference point was changing, and therefore it will have some effect on the output period or the frequency of the square wave. See, in the next time, in the next lecture, I would like to discuss another type of a comparator, which is called a window comparator. That window comparator will actually have two threshold voltages. You can choose any two threshold voltage, and thereby you can have a comparator constructed, so that whenever the input voltage varies between the two limits, the output will change, otherwise it will not change. So, this will be very useful in different applications, the window comparator, and we will also see another application of the comparator in terms of a relaxation oscillator. So, without any input you can get a square wave output by making use of the same comparator configuration, and that is what I would like to discuss in the next lecture along with the rest of the things. Thank you.